On digital computers, we have three main ways to represent signed integer values. The first is signed magnitude, the second is 1's complement, and the last and greatest is 2's complement. And that's the one we're going to talk about in this video. But before we get directly to 2's complement, I want to review the basics of what we did with signed magnitude and 1's complement. So, if you'll recall, we laid out a basic set of bit patterns for 3-bit signed values. And here are all the 3-bit patterns that we can represent. To the left is the min-term number, which is how we can identify each row briefly. So min-term 3 is going to be whatever row, when treated as an unsigned value, has the bit pattern for the number 3. In signed magnitude representations, what we did was use the high order bit, or the sign bit, to represent positive numbers when it contains a 0, negative numbers when it contains a 1, and the remaining bit positions indicate the magnitude away from 0. Now this gave us a couple problems, one of which was this weird flow as we go down the list of these numbers. We're adding one, adding one, adding one, and then suddenly we haven't got any more values within our range to represent 1 bigger than positive 3. And so the only sensible thing really is to wrap around to the lowest thing we can represent, but instead we go straight down to negative 0. So the order within the table didn't make sense to us. So we arbitrarily reordered the negative half of this table, so that at the very minimum, as we do increments, we will move down 1 row throughout the table. The only weird thing left, really, is that when we get down here and we try to do an increment from negative 0, since negative 0 is really just 0, we should go right to positive 1. So we do wrap around, but we don't wrap around to the top. We wrap around to close to the top. And that's weird, right? So we want to deal with that. Secondly, since we're coming from here, wrapping around and skipping the other 0, part of this problem, related to it, is the fact that there are 2 versions of the number 0. And so we want to do something to get rid of this. Right? So what we're going to do, similar to before when we just arbitrarily reordered the bottom half, is we're going to make another somewhat arbitrary change. We don't really want 2 zeros, so we're going to get rid of one of them. Now, positive 0 is the bit pattern all zeros, and that really seems pretty intuitive. So I like this 0, we're going to keep it. The all 1s, that is negative 0 and 1's complement, is a little weird to me, and also negative 0 just conceptually is weird, although mathematicians will tell you that 0 is not positive either. But at the very minimum, the concept of the sign bit and these other bits relating to positive 0 versus negative 0. I think negative 0 is weirder than positive 0. So I want to get rid of this one. So I'm just going to arbitrarily take the negative 1 and shift it down here where the negative 0 used to be. Now that leaves a hole here, or I would have 2 negative 1s. And I don't want 2 negative 1s, just like I didn't want 2 zeros. So to correct that problem, I'm going to bring the 2 down to here as well, the negative 2. And then to correct the obvious problem of there now being a negative 2 here and a negative 2 there, I'll bring the negative 3 down to replace the second negative 2. And then again we have 2 negative 3s, or we can think of it as an opportunity, a hole right here that we can put a brand new number. And so we will. And the only number that makes sense would be one where the value is 1 greater than or less than the things near it. Now the highest value we can represent in positive world is positive 3, so if we don't want to really think about where would we go if we add 1, instead we'll look at what happens if we subtract 1. So we had a negative 1, we subtract 1 by going up, and we go to negative 2. Go up to negative 3. Go up 1 more, well, it seems only reasonable that this be the location of negative 4. Now, of course, we're going to leave the top of this unscathed so that all the positive numbers in our representation look just like they do in the same number of bits in an unsigned representation. In fact, no matter how many bits we have, and whether we're unsigned, signed magnitude, 1's complement, or what we now have, which is referred to as 2's complement, if that sign bit is a 0, all of these versions are going to interpret that bit pattern as the same thing. So, we've made another arbitrary change to the bottom half of this. What have we gained? Well, one thing that we've gained is now we only have 1 0. And that's great. It's positive 0, and the positive, of course, is weird for us mathematicians, but nonetheless we have the 1 0. And when all the bits are 0, it's the number 0, and we just plain interpret that signed bit of 0 as meaning positive. So it's a positive 0. But we have only 1 0. Now what's also a big change here is that we have as many unique values as we have unique bit patterns. And that's not something that we've had with signed magnitude representations or 1's complement representations. So that's new. And coming right along with that is the fact that our range has actually expanded just a bit. So before, we had a range from 2 to the n minus 1, or negative 2 to the n minus 1 plus 1, all the way up to positive 2 to the n minus 1 minus 1. But that has now changed. The positive range remains the same. So if we were looking at the range of these numbers, we know that the positive end is the same. So it's 2 to the n minus 1 for n bits minus 1. So in the case of 3 bits, this is 2 squared, which is 4, minus 1 is 3, positive 3. That's the top end of our range. However, we can go all the way down to negative 4. And as that relates to a power of 2 and in terms of n, that's really negative 2 to the n minus 1. But now we don't have to add 1. We have actually extended the range. And so the bottom end of our range is a little bit different. What's also interesting here is the wrapping between minterms 0 and 7 in either direction. So look at this. If I'm here and I start incrementing, I'm going to go this direction. So plus 1 incremented is positive 2. Incremented is positive 3. Incremented, well, that's outside of our range, so we better wrap to the lowest value, like an odometer. That's negative 4. And that's right in line with the range we have here. Increment, we'll go to negative 3. Increment, we'll go to negative 2. Increment, we'll go to negative 1. And then here's the other wrap. So this is the odometer toral wrapping of values. But now we're going to wrap on minterms. When I add 1 to negative 1, mathematically, of course, I get positive 0. And that is wrapping right around to the top of the minterms rows, to which I can add 1 again and 1 again. And if I start doing the same with subtraction, 2 minus 1 is 1. 1 minus 1 is 0. 0 minus 1, well, I've run out of minterm rows, so I can wrap back around, and it's negative 1, which is even mathematically the correct answer. So we have sensical wrapping when we overflow the range of our values here, and sensical wrapping as we increment directly through the minterm rows. So as the bit patterns themselves naturally increment or decrement, everything also makes sense. So 2's complement, as a side effect of all this, is the preferred representation as dominant on all our machines today, because without the other caveats of sign magnitude and 1's complement, arithmetic will turn out to be relatively simple. Now, negation is similar, close my marker, negation is very similar to what we had in 1's complement. So what we need to do is figure out then what is 2's complement negation. it's clearly based on 1's complement negation because we manipulated the rows of 1's complement, right? So we start with 1's complement. Effectively, we just perform the 1's complement negation, which just means flip all the bits. So that's the first thing we do. And then the second thing that we do, let me bring back that slide so we can see what we were doing here. Remember how I took the 1 and moved it down, or the -1 and moved it down here, and then I took the -2 and moved it here. I shifted them all down a row. Well, what that really means from the min-term perspective, or the bit patterns perspective, is I added 1. Because here's the bit pattern for 4, and to shift from here to here, I'm going from 4 to 5, so I just added 1. To go from row 5 to row 6, I have to add 1. And to go from row 7 to 0, I also add 1, because the bit pattern 1, 1, 1 plus a 1 down here, well, that 1 plus 1, here, I'll draw it out over here. 1 plus 1, well, that's a horrible plus. 1 plus 1 is really 2. But in binary, it's kind of like in decimal when you do 7 plus 6 and you get a 3 carry the 1. It's really 13, right? But we break it up into its digits. So 1 plus 1 is 2, and in binary, that's a 0 carry the 1, because 1, 0 is the number 2. Well, 1 plus 1 again is 0 carry the 1, and 1 plus 1 again is 0 carry the 1. So we end up with this bit pattern that's 4 bits long, but our machine is only 3 bits. So when we're talking about this set of possible bit patterns, that 1 that's gone over here effectively needs to go away, and it is just thrown away to nowhere, to a void, that's affectionately referred to as the bit bucket, which I like to draw as a trash can. That's this guy. So 1, 1, 1 incremented goes to 0, 0, 0. So since we shifted all these 3 rows down 1 in the table, we effectively added 1, which means that back here in figuring out how to do 2's complement negation, we start with 1's complement negation, flipping all bits, and then we add 1. And that's basically it. So let's try this with some numbers here. Again, we'll look at our 3-bit 2's comp situation here. Let us try to take a number like 2, which is really positive 2, and then negate it. So that's going to give us the same thing as the negative of the 3-bit pattern for positive 2. And positive 2 is 0, 1, 0. Right? All right, so what we need is the negative of that now. So we're going to apply 2's complement negation where this negative exists. So it works as an operator. And that is going to give us, first, the inverse of these bits, which will be 1, 0, 1. And then we're going to add 1 to that. But we're going to keep in mind, in case our numbers go out of range, that we only work with 3 bits in this example. And so that means if we end up using any additional bits beyond the low 3, we just throw them out, put them in the bit bucket. And that way our resulting answer is the truncated bottom 3 bits. So 1 plus 1 is 2, which is 0 carry the 1. 1 plus 0 is 1. And 1 plus nothing is 1. So this apparently is the bit pattern in 3 bits, 2's comp, for negative 2. Now, of course, we want to ensure that this works in the other direction, but before we do, let's see if that jives with what we had on our table before. So we're saying negative 2 is 1, 1, 0. Let's just double check that this is the case. -2, 1, 1, 0. Excellent. We're in great shape. So what we want to do now is verify that this works in the other direction. So we would assume negation works this way because that's what we did to get those negative numbers. But we also need to feel assured that if we take the negative of -2, that we're going to end up with +2. At least that seems reasonable, right? So we're asking this question. Does the negative of -2 equal +2? Well, that really says we should take this bit pattern here, which is -2, and negate it. So we're doing the negative of -2, which is 1, 1, 0. So how do we negate in our 3-bit 2's complement machine? Well, first, we flip all the bits, and then we're going to add 1. So let's do that. Flip all the bits. 0, 0, 1. That's these bits flipped. Then we're going to add 1 to that. 1 plus 1 is 0, carry the 1, because that's 2. 1 plus nothing is 1, and 0 plus nothing is 0. And so we end up with the bit pattern 0, 1, 0, which we can interpret directly from our slide, 0, 1, 0, as a +2, because the sign bit is a 0, which means it's positive, and so the rest of the bits are effectively just the magnitude. So yes, this is 2's complement negation. And just like 1's complement, what we get from 2's complement negation is we can say that 2's complement numbers are those where when you negate by performing 2's complement negation, which is 1's complement, flip all the bits, and then adding 1, you will get a reversed magnitude, or not a reversed magnitude, you will get the negative of the value that you started out with. Great. Let's do some examples. Let's take some bit patterns as we have in the past. We'll assume a 5-bit 2's complement machine. And we'll see what we get for our favorite bit patterns. We've got 1, 0, 1, 0, 1. That's one of them. 0, 1, 0, 1, 0 is the second. 1, 1, 1, 0, 0, that's the third one. 1, 0, 1, 1, 1, that was another, and the other one was 0, 1, 1, 0, 1. Yes. All right, and then as a reminder, this highest order bit is the sign bit, and it's how we can determine initially whether or not these are positive or negative. And that really determines whether or not we can just write their equivalent decimal values, or whether we have to do negation on the bit pattern to find the absolute value so that we can then have a positive value to print out. So here, just before, we'll notice that this row and this one, each of these have a 0 in the sign bit, so these are both positive, and that means we can just solve for them right away. So this one is an 8 plus a 2, that's 10, positive 10. This one's 8 plus 4 plus 1, that's 12, and 1 is 13, so we've got a positive 13. Now for these others, these are all negative. So we got a negative number here, a negative number here, and a negative number there. But we have to negate something. So it's going to be the negative of whatever the positive versions of these are. And so we're going to have to negate this bit pattern in order to find the bit pattern that we can easily interpret, because it'll effectively be a positive bit pattern at that point. So to do that, we are going to take the inverse of this bit pattern, which is the 1's complement. So that'll be 0, 1, 0, 1, 0. And then we're going to add 1 to it. And the result of that is effectively here. We're taking the negative, what we have is a negative value with this as the absolute magnitude. So this then becomes 0, 1, 0, 1, 1, which is really the same thing as saying we have a negative 8 plus 2 is 10, plus 1 is 11. All right, let's do that on these remaining two now. So I'm going to take the negative of, and just because these are so close together, I'm going to do the addition out horizontally. 1, 1, 0, 0, or 1, 1, 1, 0, 0. Flip all those bits, so 0, 0, 0, 1, 1. Add 1 to that. That's going to give me, well, this is really the number 3. Add 1 to that, that'll be 4. So I can tell the result on this is going to be the bit pattern 0, 0, 1, 0, 0, which is the same thing as negative 4. This is 4, and there's our negative. All right, let's do that for this one. Flip all the bits. Sign bit first, so we get 0, then 1, and then 0, 0, 0. And then we're going to add 1 to that. All right. That means the same thing as the negative of 0, 1, 0, 0, 1, which is equal to negative, and let's see what this is. This is the 8-bit and the 1-bit, so this is negative 9. All right. And that's how we convert from a bit pattern in binary, when we understand it's a 2's complement representation, to its signed decimal equivalent. Now, let's do the same thing, starting with decimal and moving to 2's complement. Again, we're going to use a 5-bit 2's complement computer, or 2's complement representation. So let's do the same numbers we've done before, but now with this new representation. So we'll try 6, which is really positive 6. Negative 11, negative 13, 3, and negative 4. Okay, so let's start each of these. So the first thing I'm going to do is isolate the positive ones. They're the easiest because they're going to have a 0 in the sign bit, and then the rest of the bits will just indicate the magnitude. So I need the remaining 4 bits to be the number 6. So no 8s, a 4 and a 2, and no 1s. That one's done. Positive 3, 0 in the sign bit to make it positive. Then we're going to have a 4-bit version of the number 3, which will be 0, 0, 1, 1. 2 plus 1 is 3. So those two are done. The negative ones, however, I can't just write the bit pattern because it's not obvious what it is. And so we have to take a multi-step procedure. What we need to do, like we had done before with the 1's complement, which had a trickier representation than sign magnitude, is if I want to insert the value negative x from the decimal world into the binary world, the first thing I'm going to do is take x by itself, which is really just the magnitude. And I'm going to store it as a positive value. Then, because what I really needed was negative x, I'll perform the 2's complement negation, and that will get me the accurate bit pattern for the original value negative x. So, in the case of negative 11, what I'm going to end up doing is negating the bit pattern for 11. So what is 11 in 5 bits, positive 11 in 5 bits? Well, it's not 16, and there is an 8, and now it's not going to be a 4. It'll be 8 plus 2 is 10, plus 1 is 11. So I'm going to do that. Now, how do I perform the negation operator on this bit pattern? Well, I flip all the bits, which will give me 1, 0, 1, 0, 0, and then I add 1. And that'll give me the resulting bit pattern, which is our answer, 1, 0, 1, 0, 1. So negative 11 is the bit pattern 1, 0, 1, 0, 1 in a 5-bit 2's complement machine. Negative 13, I'll need to perform the negation operation on the bit pattern for 13. That will be 8 plus 4 is 12, plus 1 is 13. So to perform the operation, flip all the bits. That's the ones complement part. 1, 0, 0, 1, 0. And then add 1 to that. So that'll get me 1, 0, 0, 1, 1. So 1, 0, 0, 1, 1 is the 5-bit 2's complement representation of negative 13. Now we'll try the same thing for negative 4. We'll need to do the negative of 0, 0, 1, 0, 0. There's a 1 in the 4th bit. So to perform the negation operation, again, flip all the bits, 1, 1, 0, 1, 1, and add 1 to that. Now I get a 0, carry the 1, a 0, carry the 1, a 1, and a 1, and a 1. So negative 4 to binary on a 5-bit 2's complement machine is the bit pattern 1, 1, 1, 0, 0. So far, so good. But there are still a few caveats that we need to address with 2's complement. And so I want to cover those as the last part of this video. In particular, let's consider the bit pattern for positive 0. So positive 0, and I guess it really doesn't matter even how many bits we're using. For this example, we'll go back to the 3-bit 2's complement scenario, just to have fewer bits to deal with. So we'll go back to 3 bits. If I take positive 0, that's going to be the bit pattern 0, 0, 0. Right? It's positive, and so we know we can just take the whole thing as the magnitude now, unsigned. Great, we've got positive 0. But what if I want to negate it? So the negative of positive 0 is effectively the same thing as the negative of the bit pattern 0, 0, 0, which means applying the negation operation as we just did. So we will first flip all the bits to 1, 1, 1, and then we're going to add 1 to that. So that'll give me a 0, carry the 1. 1 plus 1 is 0, carry the 1. And 1 plus 1 is 0, carry the 1. 1 plus nothing is 1. But in our 3-bit representation, we're going to truncate our answer to only the bottom 3 bits. So the 1 goes off to the bit bucket, which means that the negative of 0, 0, 0 is equal to 0, 0, 0. Woo! Very mysterious. Now this is not to say that 0, 0, 0 here is negative, but if we apply the negation operator here to that bit pattern, we actually end up with the same bit pattern. Now at first, this might seem to defy logic and be bad, but it isn't. Why? Because there's no relative difference in the value. So if we take positive 0, which, because there is a 0 in the sign bit, is a positive number. But that's the only reason it has a sign at all. We must in our representation. Other than that sign of positive, the main issue here is that the magnitude away from the number 0 on our number line is 0. So it's right at the center of the number line, right on 0. Now when we negated this value, normally when we negate, like we take positive 137 and we negate it, it suddenly switches to the opposite side of the center of our number line, but the same magnitude away from 0. We just did that. We went to the other side of the number line over here, except the same magnitude away from 0, which was 0 because it's 0. So really, negating 0 and getting 0 is totally reasonable. The only thing unusual about it is the fact that our 0 has the sign of positive. So we negated a positive number and we didn't get a negative number. We got a positive number as a result. Now that might seem conceptually weird, but mathematically it's correct for us because it's still a magnitude of 0 away from 0. Still 0, right? Now, the next caveat, again, since we're on 3 bits, what I want to do is look at the extreme ends of our range. Remember, in our business here, our range now on the negative side goes all the way to -4, and on the positive side it only goes to +3. And we can easily guess that if we took +3 and negated it, we'll get -3. But what happens if we negate -4? Because there isn't a +4. So if we take -4 and we negate it, we should have some expectation. Now, for us humans, we would say that ought to equal +4, right? Okay, well, let's see how that goes. First of all, we need the bit pattern for -4. We can do this one of 2 ways. I'm going to start by going directly with the table, because we arbitrarily put the -4 here because it made sense. So that's the bit pattern 1, 0, 0. So here we have 1, 0, 0, the 3-bit 2's complement representation of -4. But we now want to negate that. So we're going to negate that original bit pattern, which means we need to take that bit pattern and invert it. So that will be 0, 1, 1. And then we have to add 1 to that. So that'll be a 0, carry the 1. 1 plus 1 is 0, carry the 1. And 1 plus 0, again, is 1. Now, we didn't have any extra digits to throw to the bit bucket, so we're just left with our result. And it turns out that similarly to the weirdness with 0, if we negate the extreme negative version of our representation, so in this case, the negation of the bit pattern 1, 0, 0 is actually totally equivalent to the bit pattern 1, 0, 0. Right? But that's not to say that this is +4. It looks like a 4 because that's the 4-bit, but only if we're using an unsigned representation. When we get this result, if we were to reinterpret what it means to decimal, we would definitely reinterpret this as -4, which means that in our 3-bit 2's comp representation, the negative of -4 is actually -4, which maybe that doesn't seem right, but that's just what we get. Now, oddly, it's still okay. And the reason it's okay is because it's correct in the general mathematics sense. It's not correct to say that if you negate -4 in human land on paper, that you should get -4. But in our computer, we have constraints as to how many bits we can hold. So it would appear that our constraints have gone against us right now, and that we've ended up with a poor representation of the value we wanted. But because the extreme ends of our representational range actually slide back and forth between the minterm rows in a consistent fashion, and when we reach the extreme ends of our minterm rows and we do increments or decrements, we wrap around the rows in a consistent fashion. We actually get values, even when they're out of range, that make sense for some basic arithmetic. So let's look at that in the context of this one. One way we could determine if this is sensible at all, because this thing here, this does not seem sensible, right? That seems like something terrible has happened to us. But what we really want to know is whether or not this makes sense mathematically in some grander context. So what if I took the negative of -4 and then subtracted 2 from that? Well, in human mathematics, at the very least, the negative of -4 would be +4, and if I subtracted 2 from that, I should get +2, right? So we're wondering if arithmetically our unusual looking value still has any kind of a function. So let's check that out. -4, let me do this on a new page. We want -4, and we're going to negate it to get +4. And then we're going to subtract 2, and our expectation is that this will be positive 2. At least that's what we would hope. So we want to see whether or not that comes true for us. So the first thing we got to do is figure out the bit pattern for these different values so that we can do the arithmetic. We need a negative 4, which means we need 4, and then we need to negate it. So I'm going to go ahead and do that. I'm just going to arbitrarily write, remember this is a 3-bit 2's comp. I'm going to arbitrarily write the bit pattern for 4 and fit it into 3 bits. Well, that would be a 1 in the 4's bit, a 0 here, and a 0 here. Now you may say, but that's not 4, that's negative 4. Well, that's true, but the best that I can do is take this value 4 that I'm seeing really as just characters and do the iterative division by 2 to find a quotient and remainder to come up with this bit pattern 1, 0, 0. And then I'll just throw away any bits that are too big. Now in this case, I don't get any bits that are beyond 3 bits. I just get this bit pattern 1, 0, 0. Now that doesn't seem like positive 4, but it effectively is positive 4. If nothing else, we could come back to here and see that the bit pattern for positive 3 is 0, 1, 1. And so if I add 1 from wherever I am, I'm just going to move in this direction. And so 4 is definitely 1 bigger than positive 3. And the bit pattern of this row is 1, 0, 0. So it actually does seem like things are coming out the way one might expect with a little bit deeper understanding. But I still only have 4. Now I need to negate that because I'm trying to find the negative 4 value so that I can negate it. Well, let's negate this, and then we'll subtract 2 from that, and then we should get a positive 2. Now let's see here. So let's negate 1, 0, 0. Flip all the bits, 0, 1, 1. Add 1 to that, and that will give us 1, 0, 0. All right, now we have negative from here, parentheses, the updated bit pattern after the negation, 1, 0, 0. And now from that, we will eventually subtract 2. So what's the negative of this bit pattern 1, 0, 0? Well, we just found the negative of the bit pattern 1, 0, 0, and it's 1, 0, 0. So that means this whole bit here gets to be replaced with 1, 0, 0. And that is our internal representation for the negative of negative 4. Now from that, we need to subtract 2. So we are going to decrement twice. Now, one way to do this is to treat this subtraction, which we don't know how to do yet in binary. We haven't covered arithmetic at this point. But we do have a sort of intuitive understanding of addition. And in mathematics, subtraction is really the addition of a negative number. So what we're going to do is take 1, 0, 0, and we're going to add to it whatever the bit pattern is for negative 2. All right, so we got more work to do. We need to know the bit pattern for negative 2. To do that first, we're going to put in the bit pattern for 2 in 3 bits. That is 0, 1, 0. And then we're going to negate it. So that's the parenthetical statement there. To negate this, I'm going to sort of come up here now. To negate this, we are going to need to flip this bit pattern to be 1, 0, 1, and then add 1 to it. Right, that's going to be 1 plus 1 is 0. Carry the 1. 1 plus 0, 1. 1 plus nothing, 1. All right, so that's the bit pattern representing the negative of 0, 1, 0. So this is the bit pattern for negative 2. We'll check it against that chart that we had earlier. Where's negative 2? Here it is, 1, 1, 0. Hey, so far so good. To this, we need to add 1, 0, 0 to complete our search. So 1, 0, 0 plus negative 2's bit pattern, 1, 1, 0. And what do we get? Well, 0 plus 0 is 0. 0 plus 1 is 1. And 1 plus 1 is 2. So that's a 0, carry the 1. 1 plus nothing is 1. But we're on a 3-bit machine, so we truncate everything beyond the first 3 bits, the lowest order 3 bits. This 1 goes to the bit bucket and is never seen again. And we can say that the negative of -4 minus 2 is equal to 0, 1, 0 in binary. And what's 0, 1, 0 binary? It's positive 2. So it turns out our question about whether or not this works out is correct. It does work out. So we're in great shape. So even though we have this weird caveat of the negative of our extreme negative value turning out to be the same bit pattern as the extreme negative value, mathematically it works out. I want to look at that again, the negative of -4 minus 2 being positive 2, as we would expect. I want to look at that one more time, but without going through all the math. Instead, I want to do it looking at our little table of 3-bit patterns. So let me bring this back over. We already know that -4 is here, right? So -4 is this bit pattern, 1, 0, 0. Now, one thing that we can do then to negate this, as we've already seen, we end up with the bit pattern 1, 0, 0 upon negation. So we do 2's complement negation, we end up with 1, 0, 0 again. So we take the negative of -4 and we're back in the same place. But then we're going to subtract 2. So before we went through all this math of converting the 2 into its binary pattern and then negating that by flipping all the bits and adding 1 and so on. But one of the nice things about 2's complement was that incrementing goes down in our minterm rows and decrementing goes up. So another thing we can do is go right to the table and just see that here we are on the negative of -4, and if we subtract 1 twice, that's the same as subtracting 2. So subtracting goes up, so subtract 1, subtract a second 1, and we've done subtraction of 2, and here we are at positive 2. And so the basic arithmetic around addition and subtraction still holds up, even though there are these apparent oddities. And so that's okay. In fact, in general, with our 2's complement representation, we can at least disregard the whole -4 and make this more generic. And we could say that for any value x that we can represent, if we have -x, if we take x and we negate it, and then we negate that a second time, that will always give us the original x. Right? And so that's good. Now, this may seem to contradict the business before of the negative of -4 turns out to actually be the same thing as -4. That may seem to contradict, but I've put these parentheses in here quite purposefully. So if we're going to apply them, then this is x, -4. This is x, -4. And so these equations don't match each other because we're missing an extra set of parentheses and a negation. Right? So up here we're saying generally that in a 2's complement representation, take any value and negate it twice, and you'll get the same value that you started with. Here we're putting in some specifics. So for our 3-bit 2's comp representation, the extreme low value -4, when we negate it, we get -4. And so when we negate it again, we still get -4. And so it works out. So 2's complement can be derived from the basic need for sign magnitude, and then getting rid of the oddities of that with 1's complement, and then getting rid of the oddities of that to have our final 2's complement. But that doesn't mean it's completely trivial to understand. It's still a very interesting representation. And in other videos, we're going to look a little bit further at ways that 2's complement just fundamentally makes sense as a way to represent values on the computer. And so I hope you will be interested and watch those videos as well.